There are times when that very weak force is considerable, and one way that we can look at that is if we look at the force of gravity between the moon and the Earth. Okay, so we'll have to look up a couple of facts here. The mass, we have the mass of the Earth, but the mass of the moon is going to be 7.35 times 10 to the power of 22 kilograms. So now we're talking about two very massive objects. The distance, the separation distance between the moon and the Earth is 384,000 kilometers, or 3.84 times 10 to the power of 8 meters. Of course, the mass of the Earth is that 5.98 times 10 to the power of 24 kilograms, and we have G. So now we can start to plug in the numbers. And one of the things that you'll notice, we've started off with this equation. So my analysis, so I'd use my equation. The force of gravity equals G times the first mass times the second mass divided by the separation between them. When we start talking about things in what we call celestial mechanics, or as they operate in space, slightly different notation. It's exactly the same thing. It's just the way that we sort of put it together, because the force is the same. It doesn't matter which one's the central body and which one's the orbiting body. But when we talk about one object orbiting another one, you'll often see the notation go something like this. We're going to have G. We're going to have the central mass times the orbiting mass all over the distance separating them. Squared. So this is the sort of way that you'd often see things when we're looking at celestial mechanics. It's exactly the same thing. It's just one mass times another mass. It doesn't matter which order I put them in. It's just that if you see these two different notation styles, this is all that it means. Is we're talking in the G mm over r squared, we're usually talking celestial mechanics. In the G m1 m2 over r squared, we're talking the general sense of the gravitational force. So now we can put in 6.67 times 10 to the power of minus 11 Newton meters squared per kilogram squared. I'm going to multiply this by 5.98 times 10 to the power of 24 kilograms, and multiply that again by the mass of the Earth, or the mass of the moon, 7.35 times 10 to the power of 22 kilograms. And then if I divide this, I'm running out of space, so let me add this here. I'm just going to bring these numbers down here so that at least we're working on the same line. I'll multiply this whole product together. I'm going to divide this by the square of that separation distance, which is 3.84 times 10 to the power of 8 meters. It's a considerable distance, but we've got even more considerable masses, and we'll square that. And now I end up with a force that's 1.99 times 10 to the power of 20 newtons. So now we can see that this, while it's a relatively weak force in the grand scheme of things, it provided enough mass that's at play here, we can have considerable forces. And of course, we would require a considerable force to hold that giant moon, that giant space rock, the moon, in orbit around the Earth. And the same would be true if we looked at the Earth orbiting the sun. The large m would be the mass of the sun. The small m would be the mass of the moon. So it is a significant force. It's the primary driving force for the way mechanics operate in the universe at large. It's just that we need lots and lots of mass to affect this force. And so that's it for the solutions that we've put together, and I've put the therefore statement here. So for your part in this, I'm going to give you some work. You're going to look at on pages 181 to 182, and you're going to look at numbers 21, 23, 27, 31, 33, and 35. Now, 21, 23, and 27, and I believe 31 are all about the force of gravity. But then when we start to compare that, now we're going to take that force of gravity, the idea of that determining that force of gravity, we're then going to use the idea of gravity, both near the surface of the Earth and perhaps away from it. But then we're going to look at this normal force is when I start to do a free body diagram with the force of gravity acting on an object. How will it interact with a surface that it's resting on given the other conditions that would give rise to it could be an acceleration of 0 or not 0, and we use sort of bring together this idea of gravity along with Newton's laws and determine what must be going on. So I'll turn it over to you. You can give those a shot, and we'll talk about them tomorrow.